Greetings everyone, and welcome to my talk about hunting bugs in JavaScript Core with CodeQL. Our journey begins when we wake up in the middle of nowhere and this guy is approaching us and start talking to us saying, "Hey you're finally awake. You were trying to find bugs in the realm of JavaScript Core, huh? Walked right into that ambush, same as us, and that hacker over there. Who are you?" So before I'll introduce myself, if you're not recognizing the following reference, congratulations, you're not a complete nerd like I do. This is from Skyrim. Who am I? My name is Assaf Sion, and I work as a security researcher at CyberArk. I enjoy CTFing and playing video games in my free time. I'm level 24, of course. Here are my character stats, so I'm somewhat skilled in CodeQL, but I'm not so skilled in JavaScript Core exploitation. My character goals are use CodeQL to find bugs in JavaScript Core, and of course have fun. Finally, my character state of mind is that I'm 100% positive and 100% excited. So without further ado, let's begin. During this talk, we'll have three major checkpoints. The first checkpoint will cover the fundamentals of CodeQL. We'll get a very good CodeQL introduction. We'll see some cool and basic examples with CodeQL, and there is gonna be even a boss fight, so stay tuned. At the second part of our talk, we'll review JavaScript Core as a JavaScript engine. We'll talk about how JavaScript Core processes JavaScript instructions, what type of JIT engines there are in JavaScript Core, and what are side effects in JavaScript. Finally, we'll talk about bad side effect modeling bugs, a type of a bug class that exists in JavaScript engines, and then finally, after that, we'll find out how we can use CodeQL to find these types of bugs. Let's begin. This is going to be a very short introduction to CodeQL, and I mean very short. This is me on the left side. What is CodeQL? For whom of you who are not familiar with CodeQL yet, CodeQL is a framework created by a company called SAML, which is now owned and developed by GitHub. CodeQL in its core is a query language. It is very similar to SQL. It lets a researcher reason with code using tools from logic. It has some cool syntactic sugar from object-oriented programming, like inheritance and class methods. We can use the CodeQL CLI. You should know that the CodeQL CLI is the CodeQL engine, which can execute CodeQL queries. So we can use the CodeQL CLI to turn code base into database. It supports many programming languages such as C++, Java, and many more. It has tons of great features to analyze code. For example, data flow analysis that we're gonna review today, but it has many more. I encourage you to read about it later. When working with CodeQL, there is a general workflow that we will usually follow. At first, the researcher will choose the open source project and make sure he can build it. After that, clean the solution and then rebuild it again, but this time use the CodeQL CLI. Next, select a bug class that you want to discover. Analyze it, understand that bug class very well, and understand how that bug class might appear in the codebase that you chose. Then, write a query that finds the bug class and make sure it works by executing that query against the prior known vulnerable version of that project you chose to analyze. That's a pro tip, so make sure that the query finds all vulnerabilities from that same bug class in prior versions. Finally, execute your query against an up-to-date database and hopefully find new bugs. Query structure. So each query will consist out of three parts that are very similar to SQL. We have the from clause. If you're not familiar with SQL, the from clause, this is where we're gonna define all the CodeQL elements that we are gonna use. Next, the where clause. Although this clause is optional, it is the very essence of your query. So this is where all the logic of your query will be in. So although it is optional, it's quite mandatory if you want to have complex queries. Finally, this is the select clause. This is where we choose how our output is going to look like. Now that we've learned what is the general purpose of CodeQL, we can start our training. Okay, who is this lovely NPC? This lovely NPC says, "Hello there, do you mind helping me with some CodeQL queries?" Sure thing. Let's help her. Our first quest requires us to find all the variable declarations in a given codebase. And this task is very simple. This is the first mini quest. So, this task is very simple. At first, we'll import C++. This tells CodeQL to use the C++ standard library that exists within the CodeQL library. We don't need a where clause in this query since we want to find all the variable declarations. So let's define the from clause. Variable, you see from variable var. So variable is a CodeQL element from the C++ library. It represents a variable declaration from the abstract syntax tree that represents our code eventually. Then we simply have to select var. This will select all the variable declarations. Amazing. So let's see. I use VS Code to run my queries, and this is how the output should look like when executing that query against a database created from WebKit. We can even click the results and review them. So let's click, for example, the host. It will take us to the actual declaration of host in the WebKit project. And indeed, we can see that this is the declaration of host. Awesome. In our second quest, we need to find all the function calls to the malloc function. This is a bit more complicated than the previous one, but not too much. Okay, so import C++, we already talked about this earlier. Now, we know that we need to extract the calls, all the calls, so let's use the element, the CodeQL element that represents every call in our code. From function call to malloc. Call to malloc is now a representation of a function call in our code base. Then, before inserting any constraints, let's select the call to malloc. If we run this query, this will extract all the calls to all the functions. So let's narrow it down by adding the where clause. Where, and then call to malloc dot get target. Get target will return the actual function that the function call element called to. And then all we gotta do is use the has name. This way we make sure that the function we called has the name malloc. And then execute the query. Here are the results. We can see that there are over 500 calls to malloc in the WebKit project. Select one, click it, and here is the call to the relevant function. Malloc in our case, of course. Okay, we have a boss fight. You think you're clever, aren't you? Find every expression that controls an allocation size. Every expression that controls an allocation size. Okay, in order to win the boss fight, we would have to use some data flow analysis. Don't get intimidated by the phrase data flow analysis. It's very simple. We would simply need to find which expressions flow into the first argument of a malloc function call. Let me remind you, the first argument of a malloc function call is the size. The malloc receives one argument, which tells malloc what's the size of the buffer he should allocate. So we want to find every expression that flows into that first argument. Again, import C++, very similar. The first part of the query is practically the same, only that we added a third element. This element called expression. It represents every expression in a code base, so it's very abstract. It contains a lot, but we're gonna use it in a more precise manner later on. Okay, now this is the first part. So right now the function call element fc holds all the calls to malloc like we did previously. Now let's use a predicate called local expression flow. This way we can define the source and the sink in our data flow analysis. Now this predicate says find all the flows, all the expressions that flow into the first argument of fc. fc is a call to malloc. The first argument of fc is the size of that allocation, and we want to make sure that source represents an expression that flows into that first argument. If you don't understand it, let's see an example, how the results are going to look like. Okay, on the left column, we can see all the expressions that control the allocation size of a call to malloc. On the right column, we can see the corresponding call to the malloc. So let's click one of the results. Here we chose a call to JS string get maximum UTF-8 string size to the size argument of the malloc call. Let's click the result. And this is indeed what it's going to look like. So we can see that by calling that function, the returned value flows into the variable JSize, which is then passed as an argument to the malloc call. Awesome. I think that was it. Yeah, that was the first part of our talk. Congratulations, that's the first checkpoint. Let's move on to the second part of our journey by entering the realm of JavaScriptCore. That's me. Hello there. So what is JavaScriptCore? JavaScriptCore is the JavaScript engine for WebKit, meaning each JavaScript instruction executed via Safari is actually handled and executed via JavaScriptCore. Now, before we'll dive into the fundamentals of JavaScriptCore, I want us to learn a little bit about side effects in JavaScript. You'll understand why we have to do it now later on. But what are side effects in JavaScript? A JavaScript operation causes side effects if it modifies the state of other variables outside the local environment of that instruction. That's a long way to define side effects in JavaScript. So let's see a more real example. Let's review it. This is an example for not triggering side effects in JavaScript. So for example, concatenating a string with an empty object. I'm sure you know the answer. A will now hold A will now have the string hello with curly braces at the end of it. That's A. A is now a string with hello concatenated with the curly braces at the end of it. But, and this is very interesting, but concatenating a string with an object that have a function, if the object has a function property named toString, this will set the value of A to something completely different. The function toString does two things. At first, it will print to the console the string side effect here, and then it will return the string BSides. Concatenating hello with this object will trigger the call to toString and will set the value of A to the string hello BSides, and of course will print to the console the string side effects here. Now, this is where the side effects occurs. The mere fact that we were able to execute a different function that has nothing to do with the concatenation, meaning that we managed to trigger side effects in JavaScript. Now, I want you to understand, this is perfectly normal. It's not a bug. It's not, a security flaw. Nothing like that. Side effects are perfectly normal. They are part of the way JavaScript works, and they're crucial to it. Okay, keep that in mind. Now, let's dive into the implementation of JS_add_nonNumber. JS_add_nonNumber is a function that written in C. It's part from the JavaScript core engine. So every time we're gonna call use the plus operator, JavaScript core will execute C code, and that C code is the function JS_add_nonNumber. This function implements adding a non-number in JavaScript core, of course. Okay. At first, JS_add_nonNumber will check if the first argument is a string. Let me remind you, the first argument is the string hello, and it is a string, so it will continue. Next, it will check if the second argument is not an object. Now let me remind you, the second parameter, the second argument, is indeed an object. So this check will return false. If it will return false, it will call a different function called JSAddSlowCase, which will call the method toPrimitive. This method will be called from the first argument. It will try to convert the first argument, which is the string hello, into a primitive object. A primitive object in JavaScript is basically a number or a string, but the first argument is already a string, which means it's already a primitive object, so nothing will happen here. It will try to convert the second argument to a primitive object. Now, this is where the interesting part happens. So when we try to concatenate an empty object, what happened is that we got a string with curly braces, meaning that the call to toPrimitive converted the object to the string curly braces. But now we have a different function in there that's called toString. toPrimitive will search for the JavaScript property toString, and if that property exists and it's a valid function, JavaScriptCore will call that function. And eventually, this is where this function is a function that we completely control, and this is where the side effects are triggered. Okay, so now that we've learned a little bit about side effects, we can focus on JavaScriptCore, as promised. So to understand the guts of JavaScriptCore, we should first be familiar with the differences between JavaScript and C. Sometimes be compiled by a just-in-time compiler. Also, C is statically typed, meaning we must declare the argument types and the return value types when writing a new function. On the other hand, JavaScript is dynamically typed language, meaning we don't have to declare anything when writing a new function. The same function can choose to handle whatever type she wants to. And finally, C allows us to have low-level controls such as direct memory management and even control over the stack or heap layout. But JavaScript is pretty much powerful for everything else. JavaScript can go fast. This is where JIT compilation comes for the rescue. There are 4 tiers that an instruction can live in JavaScript. So the first tier, we already talked about it. It's the low-level interpreter compiler. This basically takes the JavaScript instructions and compiles them into bytecode. It's not actual code that the processor can execute. It's bytecode that the JavaScript engine can execute. Then we have the baseline JIT. There is no additional logic regarding the relation between other instructions whatsoever. It simply takes the instructions, there are plenty of templates in the JavaScriptCore code base, and it will take the template. For example, we want to add 2 numbers. It will take the operation add numbers using a template, and it will produce the assembly code that represents that very function, that very operation. Next, we have the Dataflow Graph JIT compiler. At first, JavaScript core will represent a given piece of code or an operation, and it will turn it into Dataflow graph. We will then see how a Dataflow graph looks like, but it will apply several optimizations on that Dataflow graph depending on the relations between the nodes in the graph. And finally, it will compile the Dataflow graph using the JIT compiler. And the final tier is the FTL, faster than light, JIT, which highly focuses on optimizing the compiled code. It will simply take all the optimizations that the Dataflow graph JIT applied and will ignore the relation. It will simply apply all the optimizations it can to a given piece of code without taking in mind the cost it will take to do so. Okay, so let's see an illustration of how JavaScriptCore creates a Dataflow graph for a simple function. Here we have foo. Foo is very simple. It simply takes an argument. It returns the multiplication of the argument's first index property with the property y from the this object. Now, in order to compile the function using the DFG JIT compiler, we need to execute that function approximately 1,000 times. So to do so, we just put a for loop that will call that function 1,000 times. And by doing so, we will compile that function using the dfg JIT. After doing so, let's review the pseudo data flow graph created for that function. And of course, at the beginning, we set arg as the argument. Next, we make sure that arg is an array. The reason for that is that we access the first index property of arg, and therefore it must be an array. If it is an array, we're going to create and save the this object into v0, and then we will fetch the property y from this and save it under v1. Finally, we load the index property 0 from arg and multiply v1 with v2 and return it. As mentioned earlier, one of the biggest advantages of the Dataflow Graph JIT compiler is its optimizations. Redundancy elimination is a core optimization in the Dataflow Graph JIT compiler. By using the relations between the nodes in the Dataflow graph, it can determine which guards are redundant and which are not, which are crucial, in a matter of fact. Each redundant guard will be removed pre-compilation, and it will save time while executing that code. So let's take a look at the following function, which returns the division of the two properties fetched from arg. So the Dataflow graph will look like that. At first, we'll set arg as an argument. Then we'll make sure that arg is an object because we fetch properties from that argument. Then we'll fetch one argument. So for example, we'll fetch y. And then we'll check again that arg is still an object. If it is an object, we'll fetch x as well. And finally, we'll return the division between these two. If property y exists, the second check is redundant. Why? Because nothing has changed in our object, so there is no reason to make sure that it's still an object. Nothing happens. Y exists. Everything is good. Let's save some time during the execution, and that's exactly what JavaScriptCore does. But what can go wrong? If by fetching y, which could cause side effects, an attacker can change the value of arg and change it from object to a different type, then JavaScriptCore will think that arg is an object because we removed that check, and even though it is not an object, and this could lead into type confusion bugs, which could help an attacker achieve remote code execution. We know that removing necessary checks can allow an attacker to achieve remote code execution. In order to deal with that issue, JavaScriptCore must know which operation can cause side effects and under which terms. For example, adding two numbers cannot cause side effects, but as we saw earlier, adding a string with an object can indeed cause side effects, and JavaScriptCore must be aware. So JavaScriptCore must treat the argument types as well. The side effect modeling is done by the function executeEffects. You can see the full path in the slide. Under each case, that function will hold a giant switch case. Each case represents a JavaScript operation. JavaScriptCore under each case will determine if an operation can cause side effects, and if that operation can cause side effects, JavaScriptCore will call a function called ClubberWorld. So let's take a look at an example right here. This is an actual snippet from JavaScriptCore from the executeEffects function. You can see both upper operations can cause side effects according to the modeling of JavaScriptCore, because under both cases there is a call to ClubberWorld, one here and one there. But at the final operation, at the third one, we can see that the JavaScriptCore can assume that this operation cannot cause side effects because there is no call to ClubberWorld. Alright. This was the second part of our talk. We've learned that the Dataflow Graph JIT compiler can be an interesting surface for an attacker to find new bugs in JavaScriptCore. Of course, when focusing on the redundancy elimination optimization combined with side effects in JavaScript. Now let's try to make the world a safer place by hunting these bugs ourselves using CodeQL. Perfect. That's me. Now before writing new and complex queries, we should understand the bug that we're hunting as best as possible. And this tip applies to every bug you're hunting, especially if you're using CodeQL. So let's analyze together a vulnerability found in 2018 that allowed an attacker to achieve full remote code execution via Safari. This vulnerability, of course, is triggered by bad side effect modeling of the instance of operation. Let's start from the end by answering the question, how did they patch this bug? And let's understand the patch. It's very simple. Both snippets, you can see it's divided to two. Both snippets were taken from the function execute effects. The function that, as we've mentioned earlier, is responsible for modeling, for side effect modeling in JavaScript core. On the left side, we can see the vulnerable version, and on the right side, the patched one. The developers simply added a call to clubber world under the case that represent the instance of operation. This is the only line that was added to the code in order to fix that bug. So this tells us that the vulnerability is indeed around the side effect modeling that JavaScript core was doing to that operation. You can see they only added a call to clubber world in order to fix the bug. We know that the instance of operation wasn't modeled correctly. Therefore, we simply need to find how it is possible to trigger side effect using that operation. To do so, let's take a look at a part of the exploit. At first, we only need to create two empty classes. Then, we create a new object named handler that have a single function property called getPrototypeOf. Doesn't matter what the function does, this is where we're going to put the malicious exploit, but eventually it will return a class prototype. Then we replace the prototype of trigger class with a proxy object. This is very important. We replace the prototype object with a proxy object. And the proxy object now has the handler that we defined earlier. And finally, all we need to do is, of course, compile instance of using the dataflow graph JIT, and then call instance of as follows. This will trigger the bug. The reason for that is that JavaScript core already thinks that instance of cannot cause side effects, meaning that we see now that in order to trigger side effects using the instance of operation, we need to do something with replacing its prototype with a proxy object. That's the final goal of that code snippet. Let's try to understand how the operation of instance of is implemented. So this is the implementation of it that is inside the JavaScript core, meaning it's written in C. It's not the JavaScript implementation, it's JavaScript core implementation. At first it will call the default has instance, which will eventually here we'll call the method getPrototype. Object is the argument, so trigger class is our object, and the method that will be called is getPrototype. Of course, trigger class is an object, so we're gonna go to the implementation of getPrototype from JS object, and then okay, wow, what happened here? We replaced, if you remember, we replaced the prototype of trigger class with a proxy object. So the actual getPrototype function that will be called is from proxy object, not from JS object, but proxy object. And that function has a completely different implementation. This function will actually fetch the handler, the proxy object handler, and it will call the getPrototype of JavaScript function that we control, and this is where the side effects occur. Great. We are looking for, okay, so let's try to define that bug, and I hope you understood that bug. Let's try to define that bug using CodeQL. We're looking for an operation that A, JavaScriptCore would not call CloverWall under the execute effect function, and B, that function can trigger side effects even though JavaScriptCore assumed it cannot. How do we define the side effects at all? So there are three major challenges we need to solve in order to make our query useful. At first, we need to model each operation for side effects ourselves using CodeQL. Although this challenge is very interesting to solve, I've decided that we'll not talk about this in this talk because due to time constraints, but rest assured that the entire query is available in a public repo, and I added a link to that repo at the end of the slides. We'll focus on solving the second challenge, which is finding which operations can trigger side effects. Specifically speaking, we're looking for operations that can trigger side effects using a proxy object. So it's the same way that the instance of operation triggers side effects. After this presentation, I encourage you all to modify the query so that it will find other types
about strings.
Defining the side effect. This is like the crucial part of the query. So the side effect that we're looking for is constructed out of three parts. The first part receives a parameter with the type of JS object, or somewhere during the flow of that operation, a parameter will be converted into a JS object. Then there is a method call from that JS object. And finally, there must be a different method from the class ProxyObject that shares the same name as the called method from JS object. Let's remember, we want to find operation that handles with JS object. The simplest scenario is the following, where the operation receives as its input, as one of its parameters, a JS object, like here. Let's write the query real quick. We'll import C++, and we have two CodeQL elements. The first one is variable, which represents all the variable declarations, and another one, a variable access, which represents all the accesses to a variable. This way, we tell CodeQL that we are looking for a variable from the type JS object, and then all we gotta do is link the variable access to that variable. And now JS object access represents an access to a JS object variable. But what if the operation receives a generic type and it will then convert that argument into a JS object, like this? So here we see that the parameters are different from JS object, but somewhere in the code we convert base, which is a parameter, into a JS object. Okay, let's try to do it with CodeQL. At first, let's define all the CodeQL elements. We have function call, which represents all the calls to a function, and variable access, which represents all the accesses to a variable. Now that we define the expressions, let's make sure that as object will hold all the calls to as object, like here, and then we can extract its argument. We're interested in the argument, so let's link the variable, all the expressions as object arguments, and make sure that they are inside, that they are received as an argument to the as object function. This way. Then we'll use data flow analysis again to find a flow from the return value of the function as object to all the JS object accesses. Like so. The first data flow analysis is from a parameter of a JS object. This is the first argument to the argument of the function JS object, like here. And then we simply need to find the data flow using the data flow analysis. The second flow is from the return value of the function as object, like here, to every JS object access. JS object access is like this one or this one, and then we have to find the flow. If there is a valid flow in a certain JavaScript core operation, we know that somewhere during that execution, a parameter will be converted to a JS object, and this is exactly what we're looking for. Now that we found all the interesting JS object accesses, all we need to do is to make sure there is a method call from that JS object, and that there is a different method in the class ProxyObject that shares its name with the called method we found. Let's do it with CodeQL. Quick recap. By now we were able to identify every operation that has an argument which is a JS object, or somewhere in the flow of the code will convert one of its arguments into a JS object. Now we need to find if somewhere in the code there is a call to a method from that JS object. Not only that, that method must share the same name with an existing method from ProxyObject. Let's start by defining the CodeQL elements. So as usual, JS object method will represent a method from the class JS object, and this is how we can do it with CodeQL. So we basically bound the JS object using get qualifier to the JS object. So the qualifier to the get prototype method is an object, and object is a JS object. Let's bound the element from proxy. This is supposed to represent a method call from the proxy class. By the way, this is not the only way to bound from proxy. This is the way that I chose, but from proxy is an object, and we make sure that the scope of that function belongs to from proxy, a proxy object. Sorry. You can choose a different approach to achieve the same result. Finally, we want both methods to share the same name, so we compare the JS object method name with the from proxy name, like so, and eventually we need to execute it. So this will find all the JS operations that handles JS objects, and that these JS objects call methods that share the same name with a proxy object. We can now extract all the operations that can cause side effects, the side effect that we defined earlier, but that JavaScript core assumes they cannot cause side effects, and this is exactly where the bug lies in. So finally, after running our query against the database compiled from the vulnerable version of JavaScript core, we got these results. We can see that there are 4 potential vulnerable operations. One of them is indeed the vulnerable instance of, so this is a success already. But what about the rest? Although I could not approve that all 4 operations are vulnerable, I did found that the operation create this is indeed vulnerable, and this is awesome. This vulnerability was discovered by Saelo, and it shares the same characteristics as the instance of bug. So this is definitely strengthened my intuition regarding the correctness of the query. Let's have a quick recap, a summary of what we've talked about by now. That's me. We had a CodeQL tutorial. We talked about what is CodeQL, what's the structure of a query in CodeQL. We've talked about the building blocks of CodeQL, for example, variable, function call, and we even talked about data flow analysis in CodeQL. Then we talked about JavaScript core. We had a JavaScript core 101 session. We talked about the differences between JavaScript and C, JavaScript side effects, and JavaScript core execution tiers, all the JIT compilers that exist in that. And finally, we've talked about bad side effect modeling bugs. What is the potential of these bugs? How to look for them, and how to translate these bugs into CodeQL queries. If you're interested in further reading, you can of course read about a blog post that I posted that talks about CodeQL in more details, and then of course the blog post that I posted about the mysterious realm of JavaScript core, and the GitHub link to the query itself. And that's it. Thank you very much, BSides Budapest. I hope you enjoyed that talk, and I'm available for any questions that you might have via Twitter or email. Feel free to contact me, and thank you very much. Have a nice day and enjoy the rest of the conference.